Throughout video game history, programmers have always strived to create more realistic games, not only in a graphic sense, but also in the way things interact. Not surprisingly, programmers used and still use math to achieve these goals and create more enjoyable games.
Have you ever played a video game where the goal was to eliminate the opposing team?
How about when you or an object has to reach a certain point? Well, believe it or not, all of these are made possible with math.
Generally speaking, many games use physics to create realistic-looking and functioning experiences. For example, games like Assassin's Creed and Grand Theft Auto use physics to create their realistic gravity-based stunts and fights.
Games like Mario Kart use physics on turns and when throwing items.
Other realistic games, like Rocket League, similarly rely on physics to imitate gravity and how the objects, including other players, would interact with you, the player.
Specifically, video games use trigonometry in various fields, including collisions, the effect of gravity, the models and designs behind the scenes of the graphics, and the trajectory of projectiles.
Many games are highly competitive, making the accuracy of collisions between an object and a player, or a player against a player, very important.
Timing, location, and difficulty all have to be considered when programming such collisions. When looking at an object-player collision, the locations of both players, the attacker and the target, are already known and logged, but the distance between players are constantly computed.
Say that player A is trying to eliminate player B using a ranged weapon. Player B is at a height of 1 and on a length and width of 1, and player A is on a height of 1 and on a length of 1 and a width of 8. Since the height is constant, the computer won't have to consider it as a factor. Now, the space between player A and player B is 7, so the computer has to figure out, does that specific weapon that player A is using have a range of at least 7? If it does, then the weapon hits player B and gives damage.
Likewise, on a player-player collision, the location of both players are known, the distance between the players has to be calculated, and the reach of the weapon considered.
Now that you understand the basics, let's add in the trigonometry. This time, player A is using a close combat weapon to eliminate player B. Player A is at a height of 9 with a length of 1 and width of 4, while player B is on a height of 3 with a length of 1 and width of 12. Player A uses a glider to glide towards and hopefully onto, or close enough to player B to finish the job. Since the length is not only an x and y plane, the computer will have to consider the z factor. To find if the weapon makes contact with player B, we will need to find the diagonal line that connects player A with player B. To find this, we need to use trigonometry.
Looking at this situation, you can find a triangle. Plugging in the values that we know, the height, which is found by subtracting the two different heights, and the width is found by subtracting the two different widths. Now you use the Pythagorean theorem to find the unknown side. This value is the distance between the players. Same as the first example, the computer then determines the range of the weapon that player A is using and whether it is at least 10.
Also using trigonometry, you can calculate the trajectory of projectiles to create an accurate shot.
This time player A is at a height of 2 with a length of 1 and width of 6, while player B is on a height of 5 with a length of 1 and width of 10.
So, here, you would subtract the player's widths to get 4, which is one side of the triangle. Then, you subtract the player's heights to get 3, which is another side of the triangle. Now, the final side that needs to be figured out is the hypotenuse. So simply utilize the Pythagorean theorem to find the missing length, which would be 5.
How does timing, location, and difficulty tie into this? It's simple. If the timing or location is off, the chain reaction will also be off, creating an awkward experience. The difficulty connects to both the timing and location to create an overall more enjoyable atmosphere. You can raise the difficulty to create a rage-inducing game, or lower the difficulty to engage with a younger audience.
Many games are single player, and even when they are not, there is still a heavy use of automated enemies or AI/computer enemies. Having these work flawlessly is a very hard task, as we have not yet developed the technology to code machines to think like a human. Because of this limitation, we have to set up rules and boundaries to how the automated enemy interacts with the player.
Take a cannon, for example. The cannon shoots when you come into a certain range and stops when you leave it. How does the cannon know when the range is breached? And how does it know when to react? Well, it's simple, with math of course.
The cannons have a built-in radii surrounding their center to the farthest they are able to reach. When a player enters the circle's reach, a signal triggers the cannon to fire. As a result, programmers would only allow a small amount of room between the centers of the cannons without signaling an activation.
Overall, programmers rely heavily on trigonometry to code many aspects of their games. Especially in modern-day video games, players now crave for even more realistic and simulating experiences. This leads to the development of needing more ways to please the players, which are often answered with mathematical equations and theories. Without trigonometry, video games would probably still all look like Pong.
Am I